Hello, I'm Richard from Blue Sky Space. This is the second in a series of video blog posts that will discuss the key scientific, technical, and organizational facets of the Twinkle space mission and its 3-year survey program for exoplanet and solar system science. In this blog, our project scientist, Dr. Billy Edwards, will walk you through the various model mission scenarios that will inspire and drive the array of science cases for the solar system survey.
Hundreds of thousands of asteroids have been discovered, but so far only a handful have been spectroscopically studied. Uncovering the composition of asteroids is vital for understanding the formation and evolution of the solar system. And with its wide, simultaneous spectral coverage, Twinkle will be able to detect the absorption features of these bodies and will provide particularly valuable measurements of the 3-micron water feature, an observation which generally cannot be undertaken from the ground. Now, unlike the stars, which will be observed as part of the exoplanet survey, the position of asteroids changes over the mission lifetime. To understand when each asteroid will potentially be observable, the ephemeris of each object have been acquired from the JPL Horizons database and compared to Twinkle's field of regard, the patch of sky that the telescope can be pointed at any one time. The brightness of each asteroid during these observable periods has been monitored to understand the optimal window in which to acquire data. The resulting plot shows that thousands of asteroids will be bright enough for Twinkle's spectrometer to provide detailed characterization of their surfaces. To understand the number of objects that could be observed in a 3-year survey with Twinkle, the total time required for a population of objects to be studied has been calculated. This example survey operates on a brightest first policy, and all the objects that are brighter than 14th magnitude were assumed to be observed until an SNR of 100 had been achieved at 3.5 microns. For slightly fainter objects between 14th and 15th magnitude, an SNR of 50 was deemed acceptable, and these were also observed, bringing the total number of asteroids to around 2,000. These observations would require just under 3,000 hours of telescope time, including some overheads. Including fainter asteroids by extending to a magnitude of 15.5 at an SNR of 25, 3,500 objects could be studied in approximately 6,000 hours, which equates to roughly 25% of telescope time over 3 years. While a large population survey of asteroids, particularly when focused on specific family groups, will undoubtedly bring fascinating results, the study of individual bodies will also provide intriguing insights. One such object could be Apophis, a potentially hazardous near-Earth asteroid that will have a close flyby during April 2029. Now, this asteroid is going to come within the orbits of geostationary satellites passing around 36,000 kilometers from the surface of the Earth. While it will be moving too quickly to be observed during the moment of closest approach, for the week or so beforehand, the asteroid will be bright enough and moving slowly enough for Twinkle to obtain high-quality spectra, like the one shown here. This spectrum has been taken from the Relab database and the composition based off current measurements. By studying Apophis and other NEOs, Twinkle will inform us about the population of objects within near-Earth space, supporting efforts with other telescopes such as NEOWISE and NEOSIM. These investigations could ultimately help contribute to planetary defense and to asteroid exploration initiatives. Twinkle's instrumentation will also be suitable for studying comets, searching the Comet for the production of water, carbon monoxide, and carbon dioxide as the surface begins to sublimate. Characterizing these pristine objects will help develop our understanding of the origins of water and organics in the inner solar system. Monitoring the brightness of comets that enter the field of regard suggests several hundred may be observable with Twinkle. Twinkle will also be potentially able to characterize some of the new comets detected by LSST, or to help support the Comet Interceptor mission by studying potential targets.
So as you can see, the Twinkle team are putting together various scenarios of what the solar system survey could look like, but ultimately, the scientific options will be decided by the scientists who join as survey members. Founding members who joined the program before January 2021 will be invited to join the Solar System Science team and help us shape the mission. If you're interested in membership, then please contact me on richard@bssl.space. Thanks for watching.